You guys hear me okay? Wonderful. Honestly, I'd rather hear Peter talk for another half an hour. Wasn't that an incredible paper? I've been waiting for this to be published. If only he'd told me it came out yesterday, I would have read it before the talk. So I would have had a great question waiting. But I'm looking forward to reading that paper. Congratulations. It's a beautiful work. And I think it'll be a seminal work in the 21st century moving forward. So I'm going to talk today about stable isotope-based quantum effects in biological and health processes. You see there in the background the Institut du Radium, which is the original Institut Curie. It's where Pierre and Marie Curie and others started their work on unstable isotopes, using them in human medicine. In fact, I happened to postdoc at the École Normale Supérieure, which is around the corner from that now museum in Paris. And I used to go in there all the time and wonder how maybe one day in physics I could have the kind of impact that Marie Curie did. In particular, you know, she inspired a lot of other people, not only working on fundamental work herself, but also, for example, Dr. Rigaud working on medical applications of radioactivity and really doing those hand in hand. And so somehow today's talk is about working toward, you know, quantum bio with stable isotopes in such a way that it would have positive outcomes for human health. Okay. So now modern nuclear medicine, as people probably know in the room, but for, you know, folks that aren't in this area, it's sort of interesting to overview it, you know, has a number of kind of venues for unstable isotopes. For example, you know, if you look at fluorine-18 with beta plus decay, it's ideal for tracking metabolic activity in oncology, neurology, and cardiology. You know, if you look at, I think this is tertium, I'm sorry, TC, I forgot. Oh no, tertium. Help me out again.
Technetium.
Technetium, thank you. Yeah, and that was an element I didn't even know how to pronounce yet before this talk. So this uses gamma decay, and you can track organ function, for example, in bone or cardiac perfusion or renal function. And then there's the thing that I already knew about before I got into this field, which is the idea of target radiation for cancer therapy, you know, where you deposit something that is going to kill a tumor. You know, you can use this in hyperthyroidism and thyroid cancer, where these things naturally get concentrated, or you can attach them to antibodies or peptides and have, you know, tumor-specific delivery. So very advanced field. It was exciting reading about it. I love to learn about it. And I'm hoping that stable isotopes might get there as well. However, right now, stable isotopes, pretty much they do things like, you know, swap out the hydrogen for deuterons in H2O or carbon-13, and then, you know, it runs through the body, you know, comes out in some fluid or whatever, and then you do mass spectroscopy. It allows you to track things like, you know, fatty liver disease, type 2 diabetes, tumor bioenergetics, brain metabolism during traumatic brain injury. You know, there's wonderful reviews even on this topic. It has progressed, but there's some real puzzles. Okay, so I'm going to start with some empirical observations, and then we can work our way toward more and more speculative theory in quantum biology. So the first thing is that the human body, even if you don't put stable isotopes into the human body, it naturally fractionates, okay, which is kind of remarkable. Like, you might not know that your body naturally can separate out carbon-12 and carbon-13, right? And so here's a nice review on the subject. We'll come back to this in a minute. Another empirical observation is that things like the rate of ATP hydrolysis driven by myosin motors is very much dependent on the isotope. In fact, you get, you know, huge enhancements depending on the isotope. That's well established. This is a review paper from 2023. Now, there's preliminary experimental things, and I say preliminary. I don't think they're at the level of Peter's work. You know, I think he was very careful and very thorough. I don't think these are as thorough of papers, but they're great first steps, but they need to be replicated, okay? Keeping in mind that something like 2/3 of results, generally in the sciences, especially in the harder sciences like biology and medicine, are not replicated. So in anesthesiology, it's shown that nuclear spin attenuates the anesthetic potency of xenon isotopes in mice. We're going to come back to this in a minute. And also, there's some work which I think is looking very promising, and I'm now collaborating with her. This is a group of Zoya Leonenko at Waterloo, and she's looking at the effect of natural lithium and lithium isotopes on voltage-gated sodium channel activity. And so that's related to, you know, the isotope effects in the brain. Okay, so these are some empirical facts, or at least preliminary results in some cases. And let's zoom in on the first one. So this is this review on stable isotope abundance and fractionation in human diseases. So let's look at the abstract. Okay, so now the natural abundance of heavy stable isotopes is now of considerable importance in many fields, including human physiology, right? Now, this asterisk goes on to say, in fact, it varies between tissues and metabolites due to isotope effects in biological processes. That is, isotope discrimination, heavy and light isotope forms during enzyme or transporter activity. So what's going on during enzyme and transporter activity? Do we even actually know? Well, there are actual explanations out there. Okay, the most common thing is called kinetic isotope effect, which is a combination of increased bond strength, slowing down reaction velocity, and quantum tunneling, right? And then the other major explanation is transport phenomena, that diffusion coefficients scale with the square root of the mass, so you expect the mass will affect all this sort of classical diffusion. Okay, so what I want to talk about in today is that these kinds of explanations are like from a different era in quantum information, really quantum physics and chemistry, and we're in a different era today. Okay, and there are lots of things we can think about to understand what's happening even in the human body already that differ very much from these kinds of explanations, and I think they're worth looking for. So I want to remind you that the Arrhenius equation describes classical thermal activation over a barrier. Okay, this would be a barrier for, say, a reaction. And you notice that this reaction rate, and I'm just writing it with the usual notation used in chemistry, depends something on the barrier height, and then it's exponentially dependent on the temperature. Okay, it's dependent on the temperature. So it's driven mainly by temperature. Makes sense. It's thermally activated, right? Now, on the other hand, quantum tunneling, and this is the WKB expression, this tunneling rate, and I write this in terms physicists are used to seeing, so this is the attack frequency, and you notice that it's exponential in the mass, okay? So on the one hand, you have a process dependent on temperature. On the other hand, you have a process dependent on mass. So you can imagine, well, if you lower the temperature and you change the mass by changing an isotope, right, then if indeed quantum tunneling is driving any kind of chemical reaction rates, it should depend exponentially on that factor. So that's why people like to have that kind of explanation. Okay, but isotopes have spin. As Peter just pointed out, he mentioned nuclear degrees of freedom many times. That's, of course, the electron spin, nuclear spin. Combining those to make hyperfine, you have things called spin-orbit coupling, right? Where you get coupling between orbital modes in those spins. So there's a lot going on here. And so I have a long history myself of working in this field in a very different context in ultra-cold molecules. We were very surprised in cold molecules that these hyperfine degrees of freedom, really quite mattered for the physics that we measured. This is now all well established, but in 2010 it was not. I think this was the first kind of many-body paper on this subject. And here's a review, which I think a lot of people have found useful in the field if you want to know what's going on with cold molecules. Now, those of you who are chemists in the room may not be aware of this field of ultra-cold molecules and ultra-cold chemistry, which is really very interesting. Now, what about warm, wet, messy biosystems? Of course, the usual answer is, yeah, too hot, too wet, too messy, no quantum is going on. But as Peter mentioned in passing toward the end, there's something called the radical pair mechanism, which is pretty well established and measured in certain contexts. Okay, maybe not in bio yet, although you're telling me now, maybe it is well established in bio in the way that everybody believes. I mean, I'm not sure of that, but we could talk about that. But certainly in non-biological context, well established. Okay, and it involves spin orbit coupling and hyperfine or nuclear spin environment factors. These yield different G factor and Overhauser fields. Overhauser field is the effective field of the effective collective effect of the nuclei on an electron spin. And so this causes some mixing between singlets and triplets. And here's a fantastic review. I highly recommend it. I read it thoroughly myself. One thing that review describes is you can imagine you have a cement block on its side, and it's about to tip one way or the other, and a fly lands and causes it to tip this way or that way. And that's what's going on with chemical reaction pathways, in particular between two radicals. That singlet triplet mixing effect causes it to tip one way or the other. And that's, I guess, how avian sensing works, supposedly, of magnetic fields. Now, pretty famously, Matthew Fisher had these ideas where he imagined persistent entanglement in the brain. I know Matthew very well. I've discussed this topic with him thoroughly. I at first didn't believe him at all. I then got into his work pretty thoroughly. I'm not so sure this is the right actual answer for the brain, a calcium phosphate cluster. I think experiments so far have not been able to really show any evidence in this direction. However, I think the ideas in his work are totally dead on, and they're really worth reading. They're really interesting. And very importantly, for the quantum information folks in the room, he's basically using a nearly decoherence-free subspace to get persistent entanglement, in a protected environment in the brain. And I think that's the right thing to think about if you're going to think about entanglement. Now, I really want to drill down on tunneling and on spin, and we'll see what I get to at the time that I have. Did I actually start at 9:15? I don't feel like I've been talking for 20 minutes. Okay, yeah. So, all right. So just to remind you, in quantum tunneling, there's kind of three basic ideas. One is discrete to discrete tunneling, and I'm showing tunneling from a single state to a single state. This is called the Lipkin-Meshkov-Flick model. It's exactly the model that underlies the Josephson junction that's used for superconducting quantum bits. Then there's discrete to continuum, where you've got a discrete state and it can get out into this continuum. And so here's thermal hopping over the barrier, that's Arrhenius. Here is tunneling through the barrier, right? And that's quantum tunneling, okay? And then there's continuum to continuum, which if it's below the barrier, we call quantum transport. If it's above the barrier, we tend to call it classical transport. But, generally it's another kind of form of tunneling. Okay, so that's just kind of the beginning of tunneling. Actually, the way we think about tunneling today is not really like the WKB semi-classical expression I showed, or even just those three simple pictures. In fact, we think about many-body quantum tunneling. Here's a nice example from 2009 that many people will be familiar with, which is one of the three classic quantum bio examples, okay? And it was by the Spiro-Guzik group. Now, I point out that the original study is actually just using two sites. So in fact, it's actually very much looking at this. And then it just has more sites so you can hop along. It's not really continuum at all, the original study. So for example, we know that we can create environment-assisted quantum transport in artificial systems. It's not so clear that biology is doing that, right? And that's a matter of debate we could discuss. But we know we can do it artificially, okay? In terms of microtraps, it's possible to control tunneling just by flipping spins to have fermions that are the opposite spin or same spin, and then I'll push them up or down and cause them to pop in or out of a trap. That's microtrapping. In terms of tunneling, where we use interactions to bring up the possibility of quantum tunneling, that's some work I've done myself and some experiments back in 2017 together with Ephraim Steinberg. And then there are many untapped tunneling regimes to consider for stable isotopes. The first is, when we think about tunneling, we should not only think about a single particle tunneling, we should think about tunneling of quantum fluctuations themselves. If you think about a many-body problem, if I have two particles and one tunnels through the barrier, there's a relationship between those particles, right? And so, you have to think about what's going on. You can't just do a pure mean field view of what's happening. The second thing is you can think about quantum entanglement tunneling, and I just mentioned the two particle example. How does the entanglement move through the barrier? What's the transport process for entanglement? By the way, these are called Lieb-Robinson bounds in general, and the propagation of correlations in quantum systems. This is just this kind of thing in the tunneling context. When you think about tunneling, don't think about just spatial barriers, but think about tunneling through a variational landscape. A lot of times in chemistry, we call that like the energy landscape, but ultimately it's something that's variational. And then there's the idea that the many-body environment can actually enhance tunneling. Of course, this is just a single particle effect in the environment, but you may think about having more than one thing tunneling and the environment enhancing that, and that's a generally unsolved problem. Finally, I want to point out that for complex molecules, which is after all what we're interested in biology, you have different degrees of freedom, and those degrees of freedom can tunnel differently. Okay, so don't think about them all tunneling at the same time. You can think about a chemical potential that pushes you up toward the top of a barrier, and that chemical potential could be different for these different degrees of freedom because it might not be in complete chemical equilibrium across the whole system. Okay, so let's do an example. So here's glutamate mutase. This is some nice work in 2012. I learned about it actually when I was a Humboldt Fellow. Fantastic work going on across Germany. And right next door at Stuttgart was Judith Hommel doing this work. And this is very much, instanton approximation, which I'll explain in a minute. And you notice that there are these, pretty massive rate factors if you just swap out, say, hydrogens for deuterons. Okay, so this is something that you can calculate. It seems to match experimental evidence pretty well. So now in 2012, how Judith and myself would have thought about this would have been the mass, a hydrogen, a deuteron, a tritium, to use instanton approximation, which is a totally semi-classical approximation. It's a fancy word for something that is just WKB for the physicists in the room, okay? Coupled cluster and density functional theory, so sort of older tools from 20th century, and then no consideration of statistics or the nuclear state beyond the mass. Don't even think about it. How we think about this in 2025. First of all, this is an open quantum system, and you have to do open quantum system calculations. The second is that it's very easy to go beyond semi-classical. You have many particles tunneling at once. What is the relationship between those particles while they tunnel? The third is layered dynamics, that there are semi-classical, very quantum, and very classical layers within the molecule. This is somewhat like the hybrid classical, quantum classical computing ideas. And finally, we have much better tools. For example, you can use tensor networks for complex chemistry. They're very powerful methods. They can be used on systems like these. They haven't been yet. So by the way, this whole talk is a set of open problems. Okay. All right. Now, for the, DNA was mentioned right in the beginning of this session. And so I'm very happy that I put this slide in. There's this wonderful paper in 2022 on an open quantum synthesis approach to proton tunneling in DNA. Okay, and the idea is that the quantum tunneling contribution to the proton transfer rate is several orders of magnitude larger than the classical over the barrier hopping. And so it looks like maybe from this paper, and you all can debate it, that even at biological temperatures, point mutations can be driven by quantum tunneling. So I think that's a fascinating idea and well worth exploring. Okay, so let's go on to spin. I did tunneling, so I'm going to tell you about spin. Okay, so nuclear spin 101, I took chemistry long ago. Any chemistry textbook will tell you, well, reactions involve electronic states, so ignore the nuclear stuff. Okay, so that's in like chemistry 101. So that's because, nuclear states are long-lived, they're isolated. Well, things that are long-lived and isolated, we know how to quantify that now in quantum information. We quantify that by decoherence, right? So for example, for vacancy centers, you might get up to even a couple of seconds at millikelvin. I think Peter was mentioning what, microseconds in your study, right? And that had to do with some isolation effect, right, that you talked about. Okay, for cold molecules, you might even have second scale entanglement. Here's a recent paper from 2025 showing, up to 10 hours, time for nuclear spins in a solid. I mean, it's pretty incredible. So there's a huge range of possible decoherence times, depending on the situation. This radical pair mechanism is something that's pretty well established. You have evidence of it in NMR through KidNip. It's where unpaired electron precession or radicals are shifted by a spin-orbit coupling, right? And it's supposed to be behind the avian compass, as I mentioned. So I want to drill down a little bit on this radical pair mechanism because it's a pretty likely quantum effect. Okay, so how we think about it in 2025. Okay, not when it was first invented in, I guess, the 90s or something, maybe even further back. So ultimately, it's a single qubit minimal master equation model. That's what most people use. It depends on two main factors. One is, you remember the G factor, the physicist in the room that is like slightly different from 2 for the electron G factor, and you calculate those digits, and it's a tour de force calculation. It's actually not a scalar. Okay, it's a tensor because when it's in the molecular environment, it depends very much on the orbital axes. Okay, and so this anisotropic G factor is different between two radicals, and that causes some different precession rate of those electrons. Also, the nuclear environment or this Overhauser field also causes these differences. That causes a different precession rate, and that's really what leads to this effect, okay? And I would just like to point out immediately that if you insert stable nuclear isotopes into the nuclear environment, of course, the Overhauser field, which is considered often the dominant effect, will shift. So already, the radical pair mechanism will necessarily be shifted by stable isotopes inserted in the right place in molecules if it can be done. No one wants to jump up and tell me that's not possible? Okay. So now, how might you think about radical pair mechanism in modern quantum information, right? Okay, one thing is almost all the literature is doing a qubit. In fact, it's 2 electrons, and so it's a qubit. It's a dimension 4 qubit. That's the same as the exciton, by the way, dimension 4. It's a much more interesting problem, so that's right away. The second thing is to think about, the multi-qubit or more than 2 electron problem in radical pairs. Can there be more than 2 electrons that are interacting, causing this effect of the tipping of this block, like I talked about? And there we need specific molecular candidates or examples, whether it's flavins, I pronounce it correctly, or anything else. The nuclear environment is absolutely not a thermal Markovian bath. That is just not true. You can go look at the molecules themselves. It's 10 nuclei or whatever around, and they're not, it's definitely not that kind of bath, but it's often treated that way. There's a nice paper from 2018 where they start to at least do this, and you realize right away that what you have is a mesoscopic quantum system with a pair of electrons, about 10 or so, 1 to 10 nuclei, and then you have a bosonic bath around that. And so that's the more general problem that has to be treated. Okay, so now there's lots of predictions made. Here's some quantum simulation trying to run this on IBM's quantum computer. Obviously, it doesn't work well because there's terrible overhead, and quantum computers are not yet fault tolerant. Here are a couple of applications by Christoph Simon, and I think these are really nice papers to look at. And I think in the sort of NISC era, in the next 5 to 10 years, the most likely way to try to treat these things is to have an emulator. And what's an emulator? I told you that for environment-enhanced quantum transport, right, we've made artificial systems that show that effect. So we know it's a real effect. We don't really know that here. We don't fully know for radical pair mechanism in the right context of bio and all of these pieces that these things should occur. And so I think really starting to think about making a quantum emulator, something called a quantum simulator that will do this. I think that's a worthwhile experimental task. And I'm looking at key experimentalists in the room. Okay, so let's go beyond radical pair mechanism. What about the quadrupole moment? So if your nuclear spin is greater than a half, you get this extra term in the Hamiltonian. This is called the quadrupole term, right? And in particular, it has a quadrupole coupling constant. There's a gradient of electric field and a quadrupole moment, and that sort of dominates this thing. And it's key for tuning the interaction complexity in cold molecules in my own cold molecule work. So what can it do here? Well, one place to look at that is in heavier atoms. Almost all of the stable isotope studies are on lithium or something small like carbon. And the advantage of xenon is, let's look at some of these typical isotopes. So there's 9 stable isotopes. Here's 129 xenon is spin a half, 131 xenon is spin 3 halves, 130 is spin 0, et cetera. Those are very small mass differences, but very large potential spin effects. So you can swap out isotopically pure xenon, right, and think about what kind of outcomes you could get in various experiments. Okay, now let's recall that we did have that sort of empirical fact of preliminary evidence, right, with xenon in that one experimental paper that I showed in anesthesiology. Okay. Now in ultra cold molecules, in my own work, I've studied this kind of structure and how it interfaces with external electromagnetic fields. And I think that the path to study such things is laid out there and in other papers. And again, we still, even for cold molecules, we don't have a quantum emulator, let alone for warm molecules. And so I think that's worth pursuing. Okay, so I'm going to offer 3 radical alternates. I'm already at 9:46, so I'm a little nervous, but let me do at least one of them.
You have 5 more minutes.
I have 5 more minutes. Okay, so most people say tunneling or spin. Must be tunneling or spin. Probably not spin because spin's too small, even though, yeah, radical pair mechanism, probably tunneling. This is the typical answer you'll get when you talk about stable isotopes and what's going on. I would like to offer 3 alternatives. And the first is just chaotic dynamics, okay? So there are islands of stability in chaotic chemical kinetics. These can be highly sensitive to small shifts in parameters. That's a real image of a real experiment, okay? It's kind of like a chemistry context for CAM theory that people might know about dynamical systems, which is the transitioning integrability and chaos. And it depends on things like concentrations, temperature, flow rate, and maybe isotope mass or spin. This picture that I'm showing you is actually a classic example. It's the Belousov-Zaputinsky reaction. It's been well known since a long time. I think I found a problem set on this at Princeton in the 90s. So this particular picture, it's sensitive to the local relative concentration of well-mixed citric acid, potassium bromate, and a cerium sulfate catalyst. And out can come stable oscillations in period and limit cycles in spatiotemporal chaos. Now, this kind of wave is caused by a single particle of dust landing on the surface. Okay, so it's incredibly sensitive. So, of course, dust is very big compared to a nuclear spin. But is it possible that an island of stability can shift to cause very different reaction outcomes, kinetically, and that to be what's going on instead of the kinds of things I showed before with radical pair. Now, after all, radical pair mechanism is something that's very much out of equilibrium. This is an out of equilibrium kind of idea. So my first suggestion is try out of equilibrium physics. Try out of equilibrium chemistry. Okay. There is a nice example from cold atoms in which you might think, oh, that's just a long time thing, but here's a very nice short time quantum dynamics example. This is from my colleague Markus Oberthaler. I was in Germany with for some years, and I saw the early versions of this experiment. It finally worked and was published in 2017. And it's experimental observation of some things to do with movement of fixed points in a driven many-body quantum system, and very importantly, short-time quantum dynamics, okay? So thinking about how those things might persist in complex, warmer systems is an interesting question. Now, how large a spin tunneling effect is necessary to shift these islands, that's an open question, right? Now, BZ reaction, things like BZ reaction can occur in biological reaction networks. For example, calcium oscillations in cells. glycolytic oscillations in yeast and muscle cells, cell population synchronization. These are real biological phenomena where we see such kinetics and non-equilibrium dynamics. Okay, could quantum many-body chaotic dynamics play a role in chemical reactions? There's a rapidly developing field called nanothermodynamics, which is very quantum-driven. It's driven a lot by quantum information devices, and we know from those systems that equilibration happens in stages of time evolution. The first thing that happens is the decoherence of the microstate. That's the thing we're talking about in quantum computing a lot of times. Then there's quasi-recurrences. Then there's equilibration to what we call a Gibbs ensemble. And I'm sorry if this is a little bit technical for some folks in the room. This is a little bit for the physicists in the room, but I just want to clarify that we have a way of talking about position and momentum where we transform to other variables called actions and angles. Okay, and actions are like conserved quantities. And so in kind of nearly integrable systems, at first you'll get down to the Gibbs ensemble, which is based on dephasing the angles but keeping the actions. There's some onset of chaos, which is at earlier times. That's very important because we need early times for quantum effects in bio. And then there's melting to this thermal ensemble where these actions are dephased. And then finally, you get to this notion of ergodicity. Ergodicity is where you explore all of phase space. Loosely speaking, in quantum, we call this thousandless time, and I'm sweeping a lot under the rug here, but I just want to say that I grew up thinking that chaos and ergodicity are the same thing, and that's totally untrue. And you can see that by looking at this ink coming into this water, pretty plainly the interesting chaotic stuff going on is at earlier times. Okay, if I had a little more time, I would talk about driving. I think I'm short on time, Peter, so you probably want me to end now. So my other radical alternates involve driven systems, and I have some work of my own in this area, and involves something called flow adiabaticity, which is like, for those of you from optics, is like slowly varying envelope approximation. We have a carrier. The carrier is like the quantum drive. We ask, what is this in bio? And there's a slow envelope on top of that, and there's pretty fascinating emergent dynamics that can happen in such systems. And so in quantum bio, we can ask what might provide the driving field and what the envelope, okay? And then finally, had I a little more time, I would talk about emergent degrees of freedom. In the radical pair mechanism, the typical qubit that's taken is the singlet and the triplet zero state, right? So the central element is a qubit made out of a d equals 4 dimensional system. But in fact, there are all kinds of quantum building blocks one can consider. And if I had a little more time, I would talk about those building blocks. Okay, so now I'm going to conclude, so I'm not too late here, Peter. So the first is that the effect of stable isotopes on human biology are an empirical fact, okay? Because, the human body does isotope fractionation. That clearly depends on metabolic pathway. The explanation is not so clear. It's mainly speculated upon, but it's unknown. So the perspective, and this is in fact a paper that I'm writing, Peter invited me to speak on something that I have not yet actually written or put on the archive, but it's very much in my head. This is expanding the landscape of possibilities to modern quantum information concepts and tools, okay? And so I talked about tunneling-based explanation and new tunneling regimes to consider where you have some many-body effects going on. I talked about spin-based explanations, for example, testing the spin versus mass hypothesis with heavy elements, incorporating modern quantum information into the radical pair mechanism. I talked about radical alternatives, of which I had time really only to tell you about chaotic dynamics. And then finally, as I mentioned, this is a perspective for PRX Life. The board has already accepted it to go forward. This is my first time when I'm presenting this to a community like yours. And one of the reasons I'm writing this is because I go to a lot of quantum bio meetings where people are still talking about quantum physics, mainly from the 1960s and before, and often seem pretty confused about the interface with bio. So I'd like whatever I write to be useful for this community. So if you guys have feedback, I'm here for the whole meeting. I'd be delighted for you to, extremely criticize what I have to say, or to give me suggestions on other things you think might be interesting, to let me know how it landed for you. I'd really appreciate that because I'm about to write this paper. It's supposed to be a paper that's useful for others. Now, I started out with the Institut Curie, and I'm almost done. I just want to say something about my colleagues' institute, and then I'll finish, Peter. I started out with this Institut Curie, which is, so for those of you that may not be aware, nuclear physics has saved far more lives than it's ever taken, despite, Hiroshima and Nagasaki and, Chernobyl, and we can go through the list of, accidents. But in fact, because of nuclear medicine, it's been incredibly impactful on humanity. And so my colleague, Mark Raisin, who's one of my co-authors, has, something along the lines of the Institut Curie, originally Institut Radium. And so he has an institute on stable isotopes for medicine and new tests of quantum mechanics. And I just want to mention this. It's using what's called MAGIS. It's a replacement for an older method of his. It's patented. There's an actual, Nature Physics publication and an archive publication. Okay, it involves multi-resonant laser isotope separation. I mentioned when you get those stable isotopes out of the human body in blood or spit or whatever, that you have to use mass spectroscopy. So that has a lot of issues. So this is a way to really resolve things much better. Here's some of the stable isotopes that are used as tracers. Quantum atomic people in the room will recognize strontium as being incredibly useful. And so this is called the Copenhagen Center for Biomedical Quantum Sensing. It involves a couple of researchers in Europe as well, and it's already been funded by Novo Nordisk for over 20 million over 6 years. I hope that we'll have a number of quantum bioinstitutes like this around the world that have an interface of fundamental questions like I asked, and applications to medicine and human health, which is really what this meeting is all about. And what the Institut Curie succeeded in, it took a long time. It was conceived in 2009, built in 2014, started treating breast cancer in 1948, okay? And is now like the #1 place for treating breast cancer in the world, for example. So I hope that we can do something similar. Thank you very much for your time.
I guess we have time for 1 or 2 questions.
That's good.
Yeah, back there. Brigitte, maybe you can already set up your.
I thought Brigitte would ask me a hard question. She'll probably get to me later.
She still can.
Okay.
Thank you for the very interesting talk. It's a lot to absorb. But just from order magnitude estimation, when we talk about this tunneling or the chaos affecting the chemical reaction, are we talking about all the reaction products we need to think about this tunneling effect, or 1% is kind of quantum affected, or 10 to the -9 that's quantum affected? What's the argument?
So no one's calculated this in a quantum context at all. I haven't seen a single study. I looked. I did not find one.
Okay.
So the goal of this perspective is to suggest that we should not just think about radical pair mechanism and environment-enhanced quantum transport, but there are other major areas of quantum information that now become relevant to thoughts about quantum bio. And one of the key ones is quantum dynamics. So one needs a suitable set of probably complex enough set of reaction pathways to consider like this BZ, right? And then to ask, what are the real timescales in that problem? And can a spin or a tunneling effect, move that island sufficiently to get, different possible pathways? So for example, why is it that heavier noble gases are in a general anesthetic in the brain? I mean, it's a noble gas. It shouldn't do anything to the brain, right? It's actually, really, no one knows, actually. Maybe the answer is dynamics. There's something to think about.
Thank you.
Yeah. I think Marcus had a question up in front.
Just hold it out.
Yeah. Somehow maybe people in back couldn't hear. Okay, please.
Actually, there's a lot of stuff to think about, but
Yeah.
the most urgent maybe is, so in the end you propose that there's something related to chaos also, but isn't it true that in many cases quantum mechanics suppresses chaos because of interference, localization, and things like that? Isn't that the opposite of what you need?
Okay, so so right now, I was just actually at a meeting for a whole week on this. We're reinterpreting what we mean by quantum chaos and quantum many-body chaos. So that older story is maybe not so true now. Okay, so I would like to sit down with you and discuss this in depth. But basically, in dynamical systems, as I pointed out, you have many different time scales, and chaos can appear in between these different time scales. There's separation of these scales depending on the particular system. So you might have a system. So Jörg Schmiedmeier in your neighborhood has done a lot of this seminal work, where you have a system that first goes to this Gibbs ensemble and then melts and goes down later. And the time of onset of chaos can be right after this, right into this melting time.
Mm-hmm.
Okay, and so actually it's not suppressed at all in such systems. So it seems that chaos could occur in like near integral systems that are pretty cyclical as you perturb away from them.
Okay, rest is for the coffee break.
Yeah, okay. So we can discuss
Okay,
later.
great.
Yeah.
Thank you very much, Lincoln. And let's go